The P-39 Airacobra entered service in 1941 with specifications that impressed on paper. It carried a 37mm cannon firing through the propeller hub, the heaviest armament of any American fighter at that time. Its predicted top speed exceeded 390 miles per hour. Bell Aircraft and the Army Air Corps expected it to dominate in air-to-air combat. Pilots trained on it. Units equipped with it deployed overseas. And then over New Guinea and the Solomons, something became clear. The aircraft did not perform as promised. It was not sluggish in the way outdated designs were sluggish. It was unpredictable. Pilots reported loss of control during climbing turns. They reported engine failures at altitude. They reported that in combat, the aircraft became a liability. This was not a matter of inexperienced crews or poor tactics. This was a design flaw embedded in the engine configuration itself. A decision made years earlier that could not be corrected in the field. The Allison V-1710 engine sat behind the pilot, not in front. This was intentional. Bell engineers positioned it there to allow the 37 WWII cannon to fire through the propeller shaft. The configuration freed the nose for the cannon and synchronized machine guns. It also centralized mass near the aircraft's center of gravity, theoretically improving maneuverability. The propeller was driven by a long extension shaft running beneath the cockpit. On the drawing board, this was elegant. It solved the armament problem and balanced the aircraft's weight distribution. The turbocharger, however, was deleted, not for aerodynamic reasons, not for weight. It was removed because the Army Air Corps believed the P-39 would operate primarily below 15,000 feet, where a turbocharged engine was unnecessary. The decision was doctrinal, not technical. The Army expected low-altitude ground attack and interception missions. The Allison engine, without the turbocharger, performed adequately at those altitudes during testing. Flight trials at Wright Field showed acceptable speed and climb rates. The aircraft passed its evaluations. Orders were placed. Production began. What testing did not reveal, or did not emphasize, was how the engine and its placement interacted under sustained combat conditions. The extension shaft transmitted torque across several feet of fuselage structure. It was a mechanical compromise. Any imbalance, any vibration, any stress concentration would propagate through that shaft. The cooling system was also unconventional. Radiators were positioned in the wing roots, fed by air scoops on the fuselage sides. Coolant lines ran from the rear, mounted engine forward and outward. This added complexity. It also added vulnerability. But in controlled test flights at moderate altitudes with predictable throttle inputs, these factors did not dominate. The aircraft flew. It handled reasonably. It met minimum contract specifications. The design was approved. The Army issued the P-39 to fighter groups deploying to the Pacific and Europe. Pilots transitioned from older types, P-40s, P-36, expecting the Airacobra to offer superior firepower and performance. Initial impressions were mixed but not alarming. The cockpit was comfortable. The cannon was impressive. The tricycle landing gear simplified ground handling. There was no immediate sense of danger, but combat missions were not test flights. In the Pacific, the operational environment was nothing like Wright Field. Missions required sustained climbs to intercept Japanese bombers, which operated between 20,000 and 25,000 feet. The P-39, without a turbocharger, struggled to reach those altitudes quickly. Pilots opened throttles fully. They held maximum climb power for extended periods. The Allison engine was not designed for this. At 15,000 feet, power output dropped noticeably. At 18,000 feet, the aircraft was laboring. At 20,000 feet, it was barely climbing. Pilots could not catch bombers. They could not maintain formation with other fighters. They were operating outside the envelope that testing had validated. But the missions required it. So they pushed the aircraft anyway. The first indications of trouble were subtle. Pilots reported slight vibrations at high power settings. Mechanics noted oil leaks near the reduction gearbox. Coolant temperatures ran higher than expected during prolonged climbs. These were not catastrophic failures. They were signs of stress. But in a combat theater with limited spare parts and no engineering support, those signs were ignored. Or rather, they were noted, logged, and filed. There was no mechanism to feed that operational data back to Bell aircraft quickly enough to halt production or modify the design. The war was moving faster than the feedback loop. Then, over Buna in late 1942, a P-39 pilot engaged a Japanese Zero at 18,000 feet. He initiated a climbing turn to gain position. The engine lost power, not gradually. Suddenly, the propeller continued to spin, but thrust dropped to almost nothing. The aircraft stalled. It entered a flat spin. The pilot could not recover. He bailed out. The aircraft crashed into the jungle. The pilot survived and reported what happened. Maintenance crews examined his account. They found no evidence of enemy fire, no mechanical damage prior to the engagement. The engine had simply stopped producing power under load at altitude. This was the first clear failure. It would not be the last. The core problem was not a single defect. It was an interaction. The extension shaft, under high torque and vibration, began to develop harmonic oscillations. These oscillations were most pronounced during high power climbs, when the engine was operating near its limits and the airframe was under maximum aerodynamic load. The shaft was not rigidly mounted. It had to accommodate slight flexing of the fuselage structure, but under sustained stress, that flexibility became a source of instability. The shaft would resonate. The resonance would feed back into the reduction gearbox. The gearbox, already stressed by transmitting power across an extended distance, would begin to slip or bind. When it slipped, power delivery to the propeller became erratic. When it bound, the engine would load up, overheat, or seize. The cooling system compounded this. Coolant lines routed through the fuselage were longer than in a conventional layout. Longer lines meant more resistance, more heat retention, and more opportunity for leaks. When pilots held maximum power for extended periods, coolant temperatures spiked. The engine would overheat. Automatic systems would reduce power to prevent damage, but pilots, focused on the combat situation, did not always notice the power reduction immediately. They would maintain stick inputs as if full power were available. The aircraft would stall. At high altitude, with thin air and limited energy, recovery was often impossible. Testing had not exposed this because test flights did not replicate operational conditions. Test pilots climbed to altitude, performed maneuvers, and landed. They did not hold maximum power for 10 minutes while trying to intercept a formation of bombers. They did not operate day after day in tropical heat with dust, contaminated oil, and improvised maintenance. They did not stress the airframe and engine simultaneously under combat urgency. The testing regime validated that the aircraft could fly. It did not validate that the aircraft could fight. Bell engineers, when confronted with field reports, initially attributed failures to improper maintenance or pilot error. This was not malice. It was a pattern of reasoning common in aviation development. If testing showed the design was sound, then failures in the field must be operational, not structural. But as more incidents accumulated, that explanation became untenable. The failures were consistent. They occurred under specific conditions: high power, high altitude, sustained load. They occurred across different units, different pilots, different theaters. The pattern was too clear to dismiss. The Army Air Corps conducted its own analysis. Engineers reviewed maintenance logs, interviewed pilots, and examined recovered wreckage. They confirmed that the extension shaft was experiencing torsional stress beyond design limits. They confirmed that the cooling system was inadequate for prolonged high-power operation. They confirmed that the Allison engine, without a turbocharger, could not sustain performance above 15,000 feet. All of these conclusions pointed to the same root cause: the mid-engine configuration, optimized for firepower and balance, was incompatible with the operational demands being placed on the aircraft. There was no simple fix. Reinforcing the extension shaft would add weight and complexity. Redesigning the cooling system would require retooling production lines. Adding a turbocharger would necessitate a complete engine bay redesign. Each solution required months of engineering work and production delays. The Army could not afford either. The war demanded aircraft now, not better aircraft later. So the P-39 remained in service, but its role was quietly redefined. Pilots learned not to trust the aircraft at altitude. They learned to avoid sustained climbs. They learned to keep engagements below 12,000 feet, where the engine performed reliably. These were not official tactical doctrines. They were survival adaptations. Pilots shared them in ready rooms, not in manuals. If you had to climb, you climbed in stages. You let the engine cool between climbs. You monitored oil temperature obsessively. You did not push the aircraft beyond what experience had shown was safe. This was a failure of design translated into a burden on pilots. The aircraft did not fail because it was poorly built. It failed because it was built to specifications that did not account for how it would actually be used. Squadron commanders stopped assigning P-39s to high-altitude intercept missions. They used them for ground attack, where low altitude negated the engine's limitations. They used them for strafing, where the $37 cannon was effective. They used them in roles where the aircraft's weaknesses did not matter. This was pragmatic, but it also meant that a fighter designed for air superiority was being employed as a close support aircraft. It was an implicit admission that the design had failed its primary purpose. In Europe, the problem was less severe only because the Luftwaffe also operated at lower altitudes over the Eastern Front. The Soviet Air Force, which received thousands of P-39s through Lend-Lease, used them effectively, but primarily below 10,000 feet in ground attack and low-altitude interception. Soviet pilots praised the cannon. They tolerated the engine. They adapted. But adaptation is not the same as success. It is compensation for failure. Back in the United States, Bell Aircraft continued production. The Army continued procurement. There was no public acknowledgement of the design flaw, no recall, no modification program that addressed the fundamental issue. Instead, there were incremental changes. Later models had reinforced shafts, improved cooling, minor adjustments. These helped, but they did not solve the problem. The mid-engine configuration remained. The Allison engine remained. The limitations remained. By 1943, the P-39 was being phased out of frontline service in the Pacific. It was replaced by the P-38, which had the altitude performance the P-39 lacked. In Europe, it was replaced by the P-47 and P-51. The Airacobra remained in production only because the Soviet Union continued to request it, and because production contracts were difficult to cancel. The aircraft that had been expected to dominate became a footnote. The Army Air Corps did not issue a formal declaration that the P-39 was unsuitable for air combat. It simply stopped deploying it in roles where its weaknesses mattered. Fighter groups transitioned to other types. Training units kept the P-39 for advanced instruction. It was a quiet withdrawal. No scandal, no investigation, just a slow fade-out as better aircraft became available. The institutional memory of the P-39's failure was absorbed into procurement caution and testing reform, but there was no dramatic reckoning. The aircraft had failed, but the war continued. Resources moved elsewhere. Pilots who flew the P-39 did not speak of it with the reverence reserved for the P-51 or the nostalgia given to the P-40. They spoke of it, if at all, as the aircraft they survived despite, not because of. Some admired the cannon. Some appreciated the tricycle gear. But none would argue it was a good fighter. It was a design that looked promising until it had to perform under conditions its engineers had not anticipated. The P-39 Airacobra was not destroyed by enemy action. It was destroyed by the gap between design assumptions and operational reality. The mid-engine layout solved one problem: armament placement, but created others that only emerged under sustained combat stress. The deletion of the turbocharger, justified by expected mission profiles, became a fatal limitation when those profiles proved incorrect. The aircraft was not poorly made. It was poorly conceived for the war it was asked to fight. Testing validated the design under controlled conditions. Combat revealed that those conditions were irrelevant. The Airacobra did not fail because it was weak. It failed because it was designed for a fight that never happened and forced into a fight it could not win.